Hello, my name is Eduardo Benavides, and this is my video recording for my midterm exam in CSE 546. I'm in section 51, and that is the online section. So let's just go ahead and get started. So, as you can see, I have the exam prompt and my Word document that will be changed to a PDF file later on side by side. So let's look at problem one. So pretty much create that scatter plot, which I have that goes with those two, mainly those two requirements there. And my scatter plot does that in the sense of where a linear SVM with no regularization is going to make sure that boundary line is fitting all of the samples here. So even though those two green X's are close to the boundary line, without regularization, it's going to make sure that those two are still classified correctly. Um, with regularization, this boundary line could change to being like right there, right? Or still start right there, it's change slightly right there. So that'll happen because these two are so close that it'll be affected the most by the change with the regularization. So that's why this works. And again, those two green X's would be the ones that would get misclassified. So why would regularization be better than no regularization? Apologies. Apologize. That is because of the generalization that regularization brings. The generalization helps the model see unseen data better. So it's essentially sacrificing these two green X's so that if I were to give it more random points of data that hasn't even been trained on, it'll be able to classify those better. And in most cases, people want that. Next one is why is no solution A better than B? So why is no regularization preferable? It's preferable when you want it to be preferable. So doing no regularization is minimizing the training error at all cost. And for certain applications, you want a perfect classification is crucial. So let's say you have limited data, so 20 samples. You don't really care about it being overfit because you need those 20 samples to be classified properly by your model. So therefore, no regularization is preferable in that sense. So moving on to problem two, similar situation, except we're dealing with decision trees where we need to create a scatter plot where not all the samples are classified correctly when the depth is no greater than 3, but once the depth is greater than 3, all the samples are classified correctly. Um, and so as you can see for the samples circled in pink, those samples would be misclassified when the depth is not greater than 3. So it's no more than 3, right? And you can see in this picture right here, hopefully I can zoom in. There we go. A little zoom in there. In this picture right here, you can see that for this to have misclassified samples, we need leaves that aren't pure. And we have two leaves that aren't pure here. Now, in our case, a pure leaf is where the sample is classified properly. All right. And we don't have all of that with the leaves there. We have two impure leaves. So that's why this works for when the depth is not greater than 3. Now, when the depth is greater than 3, um, you see here that we now have pure leaves ending this. All right, so pure leaf here, pure leaf there, there. So it works when the depth is greater than 3, but when it's no greater than 3, it doesn't work. So that's problem two. Problem three, I'm given those two data sets right there, and I essentially have to pick a classifier that works best for them. Now, if we look at that first one, um, I said the best classifier would be a kernel SVM classifier where the kernel is an RBF. And the reason I said that is because the data isn't perfectly linearly separable. You can see there's overlapping here, but if you take a closer look in there, you can see there's a couple blue points in that cluster of orange. So therefore, the decision boundary is going to be very complex, which a kernel SVM with an RBF kernel can handle that. And the reason it's able to handle that is because it's taking that data and it's projecting it into a higher dimensional space, and it'll be easier for it to find that complex boundary. So that's why I say an RBF kernel SVM is the best choice. Now, for this data set right here, if we look at it, it's clear that the data isn't too complex, pretty simple. There is no overlapping, which is good, so that you might think, oh, linearly separable, but it's obviously clear that this is of a non-linear structure. It has a nonlinear nature. So because of that, I said the best classifier to cover this data is a decision tree. The data isn't too complex, right? No overlapping. But because of that nonlinear nature, you're going to need multiple splits, right? In a decision tree can clearly set those splits, those boundary lines, using these features here, and therefore it'll be able to classify all the data correctly. So, for example, to have a split there, and a split there, and that kind of boxes all that in there, and based on how you word your features, you classify those samples correctly. So that's why the decision tree is the best in my opinion. Now, problem 4, we got to list 3 strategies that describe and then describe each strategy and explain when it can be used and why it can reduce overfitting. So I start with regularization, and that's essentially where a penalty is being added to the cost function. That's training the model. So using L2 regularization as the example, in that one, we're essentially adding the penalty to the loss function, and that's shrinking the learned weights. And in return, it's preventing the model from assigning any too much importance to one feature alone, right? So it's really useful to use that type of thing when you have a model like a neural network that has a large number of parameters, and because it has that large number of parameters, it can easily overfit the data because it's learning patterns that don't generalize well. It's taking in a lot of noise that's not needed. Regularization reduces overfitting in this way because, like we said in the L2 case, it's adding a penalty for those large weights. So it's preventing that model, like the neural network model, from allowing all that outside noise to affect how it's going to fit the data. And that's making the model less complex, and in turn is helping preventing any type of overfitting. The next strategy I said is the k-fold cross-validation strategy. And that's where we're splitting the data into a number of k folds, and then the model is trained k times. So if a model is a four-fold cross-validation, then the model will be ran 4 times. And you can see each run as like a trial run, and if you take the average of those values, um, then you'll get a pretty good idea of how the model is acting. It's pretty good to use this strategy when you're trying to tune the hyperparameters or if you're selecting a model, right? And this is going to help reduce overfitting because the fact that it's allowing the model to be tested on multiple folds of the data, which is reducing the chance of overfitting to a specific train to validation split. Since that's happening, it's going to give a better estimate of how the model is going to perform on any new data, and that better estimate is reducing the overfit of the data. Pre-pruning is a strategy that's pretty much used purely for decision trees. Now, pre-pruning can do one of 3 things, I believe, or maybe it could do all 3, but I know it does one of these 3 things. And that can limit the depth of the tree, the number of leaves, or the minimum number of samples required to make the split. Um, in other words, it's making sure that no pure that if a tree does have a pure leaf, that's fine. The tree just can't have all its leaves be pure. So, and the reason that's the case is because decision trees, they can overfit the data by creating very deep trees. So they're essentially getting every single small detail of that tree and using it to create its fit. And pre-pruning prevents that. And so when you have a small data set and you're using a decision tree on this, you can limit the number of the max depth of that tree, right? So if max depth is 5, but it's overfitting, you can limit that to 2, and it'll be just fine. You're essentially taking away any extra noise, right? Because your model is not you're making sure your model isn't going to be getting any irrelevant noise or patterns that can cause overfitting. And so since you're doing that, you're reducing overfitting with this. So now moving on to problem 5, which I could just walk you through here, but I am going to show you the code for it. I am going to be, everything will be answered in here. Actually, I wonder if I could do this. All right, come on, come on, come on, the whole thing. There we go. Perfect, that might work. I think that works. Okay, so showing you that I get results. So pretty much, this is me loading the libraries, loading the data set, splitting the data set. This is the K-fold cross validation for the GBRT. I'm not going to run it. You can see it took 33 minutes. Excuse me. But these are the results, right? You can kind of see it here. I wish you could see it better. Yeah, but you can see not overfit, it's underfit in the beginning, and as the number of runs with the combinations increase, it's starting to become more overfit to where it's a consistency in overfit. So right after this run, after it goes to being underfit to being increasing to being overfit, like right here is when you're pretty much saying, all right, we're overfit consistently. We might have a drop here though, but we come back up to being overfit, drop, overfit. And so that's what this is looking like. So pretty much it's telling me that the model is memorizing the training data pretty easily, probably because this data is pretty simple and this is a complex model. But the best validation score comes from, I believe, this point right here. On this is marked with that black dot. So that black dot shows that's where the best parameters are. And the best parameters here is when the number of estimator is 200, the learning rate's 0.2, the max depth is 2, and yeah, that's where the best parameters are. I do the same thing for the SVM. So that was essentially the beginning of 1. This is the beginning of 2 over here. The only difference is I need to find which kernel type does it work with. Um, Pick 4 C values to test for. I do that. And I need to see how it looks on data that's not been pre-processed and data that has been pre-processed, right? So I set that up. Follows a similar idea. This is where we're getting the raw data. This is where I'm getting the standard scalar data. Um, and then we put the results in. And so this is the outcome. I can run this for you to just so you can see. It'll take about 3 seconds. I'll play again. Oh, a little bit longer. That's fine. Um, so you can see they all kind of follow the same pattern. There's nothing crazy about this. Even with the raw data and the scale data, they both have the same optimal parameters where the kernel is an RBF and the C value is 10. However, I am picking the one with the highest validation accuracy, and that is the data that's not been pre-processed. So that would be this one right here, that top one. So therefore, the optimal parameters for the SVM is where C is 10, the kernel is an RBF, and the data has not been pre-processed. So that's what I'm going to go off of. Now I do split the testing data again. So in the beginning, you saw I already split the data, and then take these two right here and I split it again. So that's what I do. Okay, there you go. So that's what I did here. And I'm getting the training times and testing times of when I train it with the optimal parameters. And so you'll see that right here. These are the results. You can see they're both overfit. And the reason they're overfit is because that training accuracy is a perfect score at 1.0, right? Again, I think that is purely because I mean, and you saw that in the SVM. I didn't really speak about it, but it's pretty much overfit always. You have that one big dip when it was testing out the RBF with a zero point zero 0.01 as a C value, right? You have that one big dip, but then it goes back to being pretty much overfit, right? So I think it's because these models are very complex in the sense of not that, and also the testing data is simple enough to where it's able to read the patterns pretty quickly, you know? So I think that's the reason why we have this overfit like this. Obviously, the GBRT is a little bit more overfit than the SVM, I would say. So the SVM has a better fit. The training time, the SVM is much quicker. Obviously, we're talking a second to less than zero point 0.2 seconds, but still it's quicker, so that's nice to have. This is just me looking at the shape for the prediction, right? Let's see. And this is me doing 1B. So what you just saw was 1A and 2A. Now we have moved on to 1B. Oh, I haven't even finished 1A because I didn't talk about the generalization. I apologize. So again, we spoke earlier about the generalization of how it gets with regularization, but generalization helps see the unseen data better. Based off this, I could add random points to either model, the GBRT or the SVM. That testing accuracy, I am confident that's going to go down. And like, I wouldn't be surprised if I add like maybe 30 more samples and maybe, and based off this training data that I give it, if I add 30 more random samples to that testing data, I'm like slightly confident it's going to be knocked down to at least like this will be knocked down to 90%, if anything, maybe 85. Like I'm very confident the testing accuracy is going to go down. So it's not good. So the generalization of it isn't the best for random data, but that's what it is. It's good for the sense that it's great at seeing the data it knows. It's bad for when it's gonna take the data that it doesn't know, that hasn't seen. Now that's been 1A and 2A. Moving on to 1B and 2B, I look for the misclassified samples in each class for both the GBRT and SVM. And to my surprise, there is none. And neither class has a misclassified sample, um, which is very intriguing. And my thought process on that is the reason it has that case is because of that training score. And this kind of shows the prediction of like, okay, let's see here. Uh-huh, uh-huh. There's not much difference between them. So that training score is really showing that, hey, we did a perfect training score. We're able going to predict this perfectly as well. Because obviously there's no misclassified samples. Now, if there were misclassified samples, so let's say 8 and 3 have misclassified samples for them. Why would that be the case? That is because 8 and 3, those two numbers share a similar curve, and that curve can be often confused with how a number is written or looks like, right? It's like 0 and 1 have two distinct shapes, so those classes are easy to uh, differentiate with, right? But 3 and 8 have that same curve on the right. So the model might get confused there. So that's why that would might be the case. But obviously our models have seen this data perfectly. So there's no problem there. So after that, so this is moving on to 1C. I create this 8 by 8 image and this bar graph right here, and they show the features importances. So you can see in position 5, 2, and 1, 4, those are closer to being a whiter color, and pretty much the whiter the color is, the more importance it has. Sorry, it's a weird sentence. The more importance it has. So essentially, at this pixel and this pixel, and you can even see at that position right there, 4, 7, at those three positions, it's essentially saying, all right, this is where If I see a pixel here, this is going to be the most useful information to make a decision on what this image is. What am I looking at? All right. Now, all of them have a similar importance value, but those three are the most important ones. So those three are essentially telling the model for the GBRT, in this case, hey, look here, you'll find a number for it. So then I went to try and use to predict proba. So this is answering number 3 to predict proba to find the correlation between the two models. However, since my kernel in the SVM is an RBF, there is no predict proba. It's not possible. You can, when I submit this, you can test it yourself. It doesn't exist. I can actually probably show you because this doesn't take too long to do. So like, let's say predict proba. Boom. I want to run this. You're gonna get an error. See, we have an error. Why? Where's the error? This SVC has no attribute predict proba. All right. And there you go. So I use predict for the SVM pretty much, right? I use the predict proba for the GBRT and predict for SVM. I do this for the target classes, which are 0, 3, and 7, and I want to split them into these 3 groups. However, there's nothing in those 3 groups. This is the relation between those two, right? And you can see that they pretty much all have an easy time looking at the samples and analyzing them. Now, this is saying that there are samples where it does have a hard time for both of them, but I look through, so I can open this in the text editor, right? This is me printing out each sample's information, and if you look through that, you can tell, no, they both are having an easy time with the samples here, right? So that means this is probably happening because all of the samples are very much easily accessible and identifiable for both models, right? And that is my one reasoning for it. And because of that, I can't really show any samples for these 3 groups. So I made a 4th group that shows the samples that are easy for both models, G4. And this is it. So this is the 0. These are 5 samples here. This is 0. This is also 0. This is a 3. You see there. This is a 7. This is a 3 as well. So yeah, I think the reason that this is happening is because, as I said before, there's 0 misclassified samples. So it kind of makes sense that both models have an easy time with the samples because they don't have any misclassified samples to start with. And I believe it's because they are reading the patterns of this data very easily. So there's not a lot of mistakes for this to have. So that makes sense, in my opinion. Weird, but makes sense. Now, for this, I do like to pick which classifier I would choose. And in this case, I would pick the SVM purely based off the fact that it is quicker and it has a better fit. Everything else it does pretty similarly or gives similar results for the GBRT, but it's just faster and a better fit. But yeah, that is it. That is all for my midterm exam. Thank you for watching. I'm sorry this has been a long one. It's been 24 minutes, but there's a lot to cover. So yeah, thank you so much. Have a good day.